Recording in
de parameter, dat is dus geen standaard type of bond. En dan zeggen we, we zullen een spoor op de nieuwe. We zullen bijvoorbeeld op de these dimensions or something dimension like some complexity parameter. In what follows, we will use some as things, not only dimension. This is parameter, okay? And then there is this operator that plays a control role in the definition of estimator of the function, okay, as we discussed last time. And this operator is defined in terms of the estimator theta hat, right? In terms of the estimator theta hat. And then we have a Markov kernel in the parameter space theta. So Markov kernel is just a function that depends, the first entry is a point in the space theta, and the second entry is a subset, right? So it tells us what is the probability of going from theta to somewhere else, okay, somewhere in set A, okay, that is what this function tells us. So it could be viewed as a transition kernel of Markov chain. In our case, this Markov kernel is defined in terms of the distribution of estimator theta hat, right? And then we around Markov chains that starts at the two parameters theta. Then at the next iteration, according to this formula, it will jump to
change it starts.
At the next iteration, it jumps to theta hat 1, which is just our estimator theta hat. So it means that we sample the data x1, xn, right? Observations x1, xn from distribution with parameter theta, right? And create an estimator theta hat. And this will be where our Markov chain is at moment of time 1. And then what we do next in order to follow the same transition kernel, we would have to resample the data, right? And resample an observation from the distribution with parameter theta hat. Okay, and this is what is called in statistics parametric bootstrap, right? And then we create new estimators. This will be already bootstrap estimator, and this is theta hat 2, and then again we do the same. We use this theta hat 2 as new value of the parameter, right? And resample and create another estimator. This will be already the second iteration of bootstrap, right? And we continue like this, right? And this is exactly just Markov chains that start at theta and evolves with this transition kernel. We see that, right? We see that. Okay, so that's kind of the object that is of interest here. Then we discussed last time that we have to deal actually with powers of operator t, okay, t to the power k f of theta, right? And it will be just equal to expectation of f of theta with hat k, right? So it will be expectation of the state of Markov chain moment of time k, right? And function f went to the state of Markov chain at moment of time k. It's just standard, simple fact about Markov chains. And then we are especially interested in this operator b to the power k. So b is t minus identity. Okay, b is t minus identity. And b to the power k f of theta by Newton-Leibniz formula can be written now in this form, right? Can be written in this form. And t j of t to the power j of theta is the expectation of f of theta hat j, right? It's expectation of this guy. So we can now pull out expectation, and we are ending up with this expression, right? With this expression. And this expression is case order difference of function f, okay, on the Markov chain. Right, so we apply our functional f, right, to Markov chain, and the case order difference of this sequence will be given by this formula. So this is average case order difference. We can also, kind of, you remember that we defined some function fk that is defined as some alternating sum related to the sequence b to the power jf, right? This is Neumann series, right? Truncated Neumann series that we are using in order in order to solve approximately integral equation T G equal to F, right? And to construct estimators that will have small bias, right? As a result. Okay, and this function fk theta can be written by simple combinatorics in this form. This coefficients, right? And we kind of compute f at along our Markov chain, right? And we need only a segment between 0 and k of Markov chain, right? And in principle, we can use this relationship in order to evaluate value of fk at estimator theta hat using a result, right? Using Monte Carlo simulation, right? Because when we do this bootstrap type of thing, we can use sampling and compute it with replace expectation by averages, okay? And this was actually the kind of using bootstrap in this context was the initial idea of Hall and Martin and they were not interested in high dimensional problems, where we were interested in using bootstrap or minus function. Okay, so now I mentioned already last time that there is some similarity here with very simple problems in standard calculus, right? These are problems about finite difference operators. Okay, so if you use delta HF, it's kind of a discrete differentiation, right? We take small scope A, step H, and compute the increment of the function when we move from x to x plus h. Then if we kind of apply this operator k times, so compute delta h to the power k, it will be given by this formula that looks exactly the same as the formula we had on the previous slide, right? The previous slide, just the motion is different. Instead of this Markov chain, we have this deterministic motion along the grid, right? And this is case order difference of our function, and case order difference for function of smoothness k will be of the order h to the power k. Of the order h to the power k. So in our case, the step is of the order square root of d over n for our chain. These are the size of jumps on average. And we might hope that because of this similarity, we will end up with the size of this operator of the order square root of d over n. We need to justify it. Okay? So we already saw that this is true in the case of a very simple version of this when we dealt with location models or random shift models, right? This we already had something like this. We did not use the language of bootstrap chains, but they are there anyway. Okay, despite the fact that we use it just simple. Okay, so the idea here will be to, in some sense, reproduce the same argument that we did in the case of location models, okay? But in this case, this argument will be more complicated, and it relies on certain notions that I will call random homotopy, okay? It's sort of abuse of language because homotopy has topological meaning, okay? It's a notion from topology. There is some similarity to what is written here, but it's a notion from topology. Here we don't care about topology; it's probabilistic notion for us. Okay, so what will be random homotopy? So we are considering a stochastic process that has two variables. One variable is a point theta in the parameter space. Another variable is a number t between 0 and 1. So it's t can be viewed as time. Okay, and then there is spatial coordinate and there is time. Okay, and then this function is random, as I said, and with values in theta. It's a stochastic process. Okay, that evolves in theta like this. Okay, and then we will call such stochastic process a random homotopy between parameter and its estimator theta hat. Okay. If the following two properties are satisfied, this will the moment of time 0, this function is just identically equal to theta, and at the moment of time 1, at the moment of time 1, this function is equal in distribution, has the same distribution as estimator, provided that the data is sampled from distribution with the parameter C, okay, with the parameter C, okay. So that's random homotopy, okay, what I will call random homotopy between parameter and estimator. So in some way, it's certain coupling, okay, certain random deformations that allow us to go when time goes from 0 to 1, from the parameter to a random variable in the parameter space that has exactly the same distribution as the thing. Okay, as estimator. So we are kind of trying to create couplings that would allow us to obtain random variable with the same distribution as estimator by some deformation. Okay, we will. It's not a part of the definition, but we will. You will see later that we will need this function to be smooth, both with respect to t and with respect to c. Right, so with respect to both variables. Okay, so it's a smooth deformation. Okay. Okay, so now a couple of examples of such random homotopy. So if we go back to location model, okay, to location model, or I again wrote you location model is location parameter we want to estimate it observed in some noise whose distribution does not depend on the location. We are using a covariant estimator, so we can write theta hat as theta plus psi, where psi is kind of noise also, and kind of think about this now as a just single observation, right, of theta. So we can replace the data by the single observation if you wish, right? And then kind of the definition of reasonable random homotopy in this case is very simple. It just will be theta plus e psi, right? At moment of time 0, it's coincide with theta. At moment of time t, it's coincides with theta hat. We won't even talking about coupling, creating the same distribution, it just coincides. Okay, so, it's kind of very simple. That this is the simplicity is the reason why we did not need even this notion. Okay, when I wrote what I wrote last time. Okay, that's the case of location model. But this is another example, and this is we will use today at some point. Okay, we will need this random homotopy. This is about IAD observations from kind of general normal model. Okay, so the parameter space in this case will be RD times the cone of covariance matrices, right? The cone of all covariance matrices. The estimator that we will use will be just this couple. Our first component is x plus bar, and the second component is standard sample covariance, right? Standard sample covariance. In this case, we can create a random homotopy this way. We can create IID standard normal data in our d-dimensional space, Z1, Zn, and create sample mean and sample covariance based on standard normal data, right? And then we can rescale the mean, right? We add mu and multiply by sigma 1/2, and then it will have the same, exactly the same distribution as mu is hat, right? And we can multiply by sigma 1/2 on both sides, sigma hat z, and then it will have exactly the same distribution as sigma hat, okay? As sigma hat based on our data, right? Based on our data. So this is will be a perfect random homotopy. At moment of time 0, it coincides with the parameter, right? It's equal to theta is this couple with sigma. At moment of time 0, it coincides with mu sigma. And at moment of time 1, it's equal in distribution, right? We created a coupling such that it's equal in distribution to our distribution. Okay? Now, you might see that unlike the previous example, there will be already some trouble with the smoothness of this metric. Okay? And this trouble is related to the fact that we are using square root of the covariance, okay? And if the covariance square root is not, of course, continuous function at 0, right? And if the covariance, not smooth function at 0, right? And if the covariance has eigenvalues that are close to zero, we will be in trouble with smoothness of this mapping. Only when the spectrum of the covariance sigma is bounded away from zero, we will be okay. Okay, otherwise, there will be some trouble with Guldog norms of this mapping, and as we will see, Guldog norms are important in this problem. So that will be a constraint for us, okay, when we use it, okay, but that's the nature of the problem. Okay, now I can have this here another example that I probably will not discuss. It's kind of general construction of sort and random homotopes and some problem using what is called Mozart count. Okay, so I'm not going to use it in my follow, so that may just skip a couple of slides. Okay, so that's examples. What is more important for us is to understand how we are going to use random homotopes. We are going to use random homotopes in order to obtain some representation of the bootstrap chain. Okay. We want to represent bootstrap chain now in terms of superposition of certain random maps, okay, independent random maps. And namely, we will do this. We will assume that we have a random homotopy H between parameter and its estimator, okay, which was defined before, right? And then what we will do, we will create IAT copies of this random homotopy. This random homotopy H. We have IAD copies of H, H1, HK, and then we will create a superposition, right, of these guys. And the superposition, you know, in the case when K is equal to 3, is written here, okay, explicitly written here. That will be what we will get in this case, okay? That will be what we will get in this case. So it's a superposition of some functions that supposedly are smooth, defined like this. Now this GK is now defined on theta times k-dimensional unit cube. Okay, that's the domain of this new stochastic process. Okay, this new stochastic process. If we look, by the way, at location model, okay, then GK of theta T1 Tk will be equal exactly to theta plus T1 psi 1 plus Tk psi k. Okay, it will be very simple. Okay, like this, where psi 1 psi k are IID copies of random variable psi on the noise of this random shift model. Okay, on the noise of this random shift model. Because in this case, we have something really simple. Okay, that will be this thing. Okay, in general, it's could be something more complicated. Okay, could be something more complicated. And then this is a very simple proposition. Okay, that I'm not going to prove, but you can easily prove it on your own. Okay, that tells us that if I create this sequence theta k tilde, which will be gk of theta, and I fix all variables, make them equal to 1. In this case, I'm creating a copy of my Markov chain. It has the same distribution as bootstrap chain. Okay, so this is representation of bootstrap chain, a superposition of random homotopes. Okay, a superposition of this IID random homotopes. Why it has the same distribution as bootstrap chain? It's easy to check that both chains we are assuming start at the same point theta. Okay, the starting point is theta, and the transition kernel for this chain theta k tilde is exactly the same as the transition kernel for our bootstrap chain, and this follows from the definition of random homotopes. So I don't know if you can practice this way. Moreover, you know, if you take a vectors of unit cube, so a binary vector, right, with components T1, Tk, such that there are exactly J components equal to 1, and the rest of the components are 0. Okay, the rest of the components are equal. Then theta hat j will have the same distribution as gk of theta t1 tk. So in fact, when we look at these vertices of the unit cube, there will be many copies, okay, that we can use, right, of this of these guys in our bootstrap shape. Okay, many distribution of this, okay. Well, in this case, k choose j to be precise. Now we can. I am making a couple of claims that immediately follows from what I said. Okay, operator tk f theta, which is equal to this, right, will be can be represented now this way. Right, we can represent it this way. That's obvious. And then, moreover, for all j less or equals than k, we use this binary vector with exactly k non-zero components. Then tj f theta can be also written as this expectation. Okay, and there are k choose j again vectors with this property, right? With this property. Now I claim that we will have also certain representation for operator b k f of theta. This is very crucial operators for us because, as you remember, the bias of estimator fk of theta hat can be written in terms of k plus first power of operator b, right? So it's tells us that we need to know the size of this, right? And it turns out that you can write it as this expectation now in terms of this representation of bootstrap chains that we have. Why this is true? In order to prove it, I need just to repeat the argument that I already did in the case of location model. Okay. Was exactly the same argument, okay, nothing changes, okay, the argument. We start with, we look at operator b to the power kf of theta, t minus say, hey, we use Newton's binomial formula to write it this way, and it's written as an expectation of, here I have expectations of function f computed along the bootstrap chain, right? And now I replace this, right, by this expectation, right, where vectors t1, tk are such that there are exactly j non-zero components. And the number of those vectors is k choose j, right? And all those expectations are the same, so we have the same sum. Then we can pull out expectation. We are getting some alternating sum of function on the vertices of unit cube, right? And this is exactly the application of discrete differentiation along the sides of the cube, right? There are k dimensions of the cube, and we differentiate in discrete sense with respect to any dimension, and then by Newton-Leibniz formula we can write it as expectation of this integral of the case mixed derivative of this function here, right? Okay, so that's what we did yesterday in the case when our homotopy looked like this. Okay, when our homotopy looks like this, it was immediate to write down what it is. Okay, it was immediate to write down what it is because it was a very simple function, right? We immediately differentiated it and computed this derivative and wrote it. Here it's a bit hard, okay? Why it's a bit harder? Because now what is written here is superposition of k plus one function, right? We have k random homotopies, right? We have k to the superposition. And we, on the top of it, we use only also smooth function f, right, or functional f, right, and we created this thing, right? Well, now we have to differentiate k times with respect to this variables t1, tk, this superposition, right? Since all of us studied some calculus, okay, we probably know in some detailed calculus book about the existence of this formula, okay? This is a formula that usually attributed to Francesco Flauer di Pro, okay, 19th century Italian mathematician, a student of, who when he studied in Paris was a student of Cauchy and Leverrier. Leverrier was French astronomer, much more famous at that time than Cauchy, because it was at the time when Vladimir just predicted the existence of a new planet, okay, of Neptune. Okay, and when he predicted it, he wrote a letter to German astronomer Halle, and Halle indeed observed some Neptune, right? And this was a big deal at that time. Okay? So Vladimir studied some analysis with Cauchy, apparently, and studied some celestial mechanics with Leverrier. Did some work in both directions. And so about soon after he finished his studies in Paris, he published this paper in 1855, where there was this formula written in a completely different way, okay? And it's a 2 pages paper, but if you look inside, you will see that it's hardly more than 1/2 of a page, okay? There is just some formula written in the form of some determinant. It's called nowadays determinantal form, Vladimir formula, okay? And there is proof in the case when k is equal, n is equal to c, okay? And then he writes that general cases is that's it, no references, okay? And he was not the first one. There were people who discovered this formula earlier, and there was even a textbook on calculus by Arbogast, I guess, that was published in 1800. Already had sexual electron with this formula, but Arbogast was 18th century mathematician as a student of Cauchy. Probably Vladimir did not look even in those books because they were very old-fashioned at that time for people who studied with Cauchy. Okay, so he did not know this for sure. Okay, so it's so you know his spectral. He was Cavaliere Francesco Vladimir. He was from aristocratic family, Italy and Piedmont. It's the youngest son in this family, so he did not inherit any higher titles, but his brothers were counts. That way, those titles were higher than counts. Anyway, okay, here's an interesting guy. So now, when you know, if you look at the formula, you immediately see that we are dealing with combinatorial problem here. It's typical combinatorial problem because when you start applying chain rule to superpositions, right, you kind of immediately are getting to some combinatorics. It's higher order derivative. In our case, it's even, you know, superposition not just of 2 functions, but of many functions. Okay. Now, okay, what will happen in our problem with this kind of Vladimir type calculus? Okay. It turns out that you can derive a formula, maybe a bit complicated formula for operator bk of theta. It's a bit complicated, but it's still a formula that is usable. You can, for instance, if you wish, you can further differentiate it. Okay, it's kind of some integral representation for operator bk of theta, much more explicit than we had on the previous slide, where it was just expectation of the derivative. Okay? So what is happening here? It turns out that you can represent this guy as a sum parameterized by certain partition trees on the set of variables. Okay, well, these problems are k variables. In our case, I chose k to be 4. Okay, so you're looking at certain partitions, okay, of this variables. For instance, in this case, I decided to divide this set of variables into 2. It's 2, right? And then something happening here because the last variable always disappears. Okay, beginning from this level, start disappearing, right? When we move to the next level, and at the end, we are left just with 1 variable. Okay, but with 1 variable. This has to do with the structure of our superposition, because if you look at our superposition, there is 1 variable T4, for instance, in this case, it will be at the very end, okay? And then when you start differentiating, you will differentiate F, right? And then inside of F, there is H4 of something that is superposition on itself, and then T4. And then in order to differentiate, when you are applying chain rule, you would have to take some derivative of F. and then differentiate with respect to two variables that are inside. One variable is complicated, it's itself superposition, another variable is T4. And after you differentiate it with respect to T4, it disappears. It's not any longer inside the next superposition. That's why we have to deal with such type of trees. Then there is certain way to label these trees with differential forms, okay, with certain derivatives. For instance, I chose a tree in which I divide into two sets. It means that I have here to put second derivative of function f on the top, right? Second derivative of function f, and then it will be bilinear form with two entries, right? And one entry will be this derivative, another entry will be this derivative. There is some algorithm after it is done, and you can discover this algorithm if you just carefully follow the chain rule and do it by induction. Okay, so it's kind of the way I, for instance, discovered it for myself. And then what you do at the end, you kind of these forms are defined in such a way that you can create a superposition of these forms. So forms will be substituted one into another, right? So you have this complicated expression gives you what I would call the partial derivative of this thing in the direction of this particular t. And then you have to end up these things over all things of certain structure. Okay, that's basically the formula that you can derive. Okay, it looks a bit complicated, but this multilinear form are easy to handle. You can find upper bounds on them, right? And then you will end up in the upper bound with certain derivatives of these guys, right? And these guys are independent one of another, and you will get product of independent things. You can start computing expectations, right? Because you or a bounding expectation, right? Because this is what you get in the situation. Okay, that's basically how this calculus works with this type of problems. Okay, and using this technology, okay, using that technology, you can start moving upper bound on operator VK FC under reasonable assumption obtain bounds of the order we want to get, say of the order like this, right? And we are in business. We can start controlling bias, right? Obtain the bound of the bias for functionals of smoothness CS, right, for our estimator, exactly of the type we, right? That's basically how it works. It's some work. Okay, but what's maybe was the most complicated calculus exercise I did in my life. It's calculus. Okay. Anyway, so you can develop this technology and use it at your pleasure. Okay. Okay, so now I'm moving to the next section of my talk, and I will look still at the same method, but I will try to show you some final results in several problems in which I studied this method. Okay, in 3 problems in which I studied this problem. This will be the next thing we will discuss today. So here, my main tool will be concentration and equalities. Okay. Concentration and equalities. And in order to write, because we already more or less figured out how to handle bias for these estimators, right? So that we are studying, right? And now the next step is to try to study concentration, okay, for these estimators. Okay, to write concentration and equalities, it will be convenient for me to use the language of Orlich norms. Okay, so we are looking at some function, I will call it loss function, because this will be the role of this function in the statistical problem we study, which is convex on degrees, okay, and equal to 0 at 0. Then the Orlich norm, psi norm, is defined by this expression, and the set of random variables for which the norm is finite, right, is space L psi of P, right? This space, okay, that we have here, okay. This is a generalization of LP spaces, right? In the case when psi of u is u to the power p, when p is greater or equals than 1, this definition gives us LP space. Okay, gives us LP space, easy to check. And but there are other popular choices. One choice is psi1 norm that allows us to kind of finiteness of Orlish norm. Orlish psi1 norm will tell us that our random variable has some exponential tails, and we can write exactly the inequality in what kind of tail behavior this random variable will have, right? And there is psi2 norms that correspond to some Gaussian tails, right? That we, if we psi2 norm is finite, we can write inequality of some Gaussian type for our random variable, okay? That's basically how it is used. We can look also at psi alpha of u for arbitrary alpha larger than 1, for alpha smaller than 1. This function is not convex, so it's not, so this thing is not does not define a norm, right? But you can prove that for alpha greater or equal than 1, this psi alpha norm will be equivalent up to constants to this norm, okay? So that is defined basically in terms of the rate of growth of LP norms. Okay, so it's related to how fast LP norms grow. Okay, and this definition makes sense for alpha smaller than 1, 2. So we have the whole scale this way, right? There is a way also to modify the definition of psi alpha function for alpha less than 1 so that it becomes convex and gives you the same thing. Okay, but it's kind of very convenient to switch to this language of LP norms, and I will be doing this a lot. Okay, how fast they grow, this tells us what kind of tails are variable. Okay. Okay, finally, I will use this ordering of losses. Okay, this ordering of losses defined by this expression, and then we have the whole scale of losses. Okay. The smallest one will be L1 norm, corresponding to L1 norm, right? And just integrability of our random variable. And the largest that we will use will be psi2, but you can go further if you wish, okay? So that's basically what we will use, okay? To talk about concentration in these problems. Okay, I will start with Gaussian location model. This is the simplest model because we will directly use Gaussian concentration inequality in this case, which are very well developed, okay? So again, we have standard location model, our parameter is theta, and then we are ready we are observing it in Gaussian modes, right? It can be done in arbitrary Banach space, that's not matter, okay? Everything is the same regardless of what linear space you are, it should be Banach space, okay? Then we have, there are actually two ways to characterize the level of noise in this graph, right? Two basic ways. One way is to use something like this. So it's kind of supremum over all EU of norm less or equal than 1. U is should be in dual space 2E, right? In dual space 2E. And if you look at the supremum, you are looking at maximal variance of linear function, right? Of psi, okay? Maximal variance of linear functional and linear functional is not bounded by 1. Okay, is not bounded by 1. This is exactly the same that as this supremum for bilinear forms of covariance operator of psi. Okay, of covariance operator of psi. We will talk in more detail about covariance operators later, but I will be using covariance operators here, right? And this is the covariance operator norm of covariance operator. So this is, I will call it V covariance, okay? This will be supremum of variances of linear functions like this, okay? Another option is to look at expectation of the square of the norm. That can be written this way. So the difference is that we now move supremum inside the expectation, right? This I will call strong variance, okay? I will call strong variance. If your noise is just standard, let's take not standard normal, but let's take normal, which means 0, and covariance matrix is sigma squared times identity, right? In this case, weak variance will be equal to sigma squared, and strong variance will be equal to sigma squared times d, times the dimension of the space, okay? It will be exactly the expectation of the square of the norm in this case, right? Now, the ratio of strong variance and weak variance in this simple model will be equal to the dimension, right? In general, I will call this effective rank of the covariance, okay? And we are going in what follows to deal a lot with this quantity, but I will get back to its definition later, okay? The ratio is effective rank of the covariance. It's kind of a dimension type quantity that you can use even if your space is actually infinite dimension, okay? Okay, so this is our option. Okay. Now, let's talk about Gaussian concentration a little bit. There are many ways to write, to derive Gaussian concentration inequalities. I will use the following approach. I will assume that I have some functional on E, real valued, that is locally Lipschitz. Locally Lipschitz or Lipschitz in any ball shape. Okay, in the space, and then what I will do, I will define local Lipschitz constant. This function is defined this way, so it's infimum over all neighborhoods of x, right? Of Lipschitz constants of our function in the neighborhood, right? In the neighborhood. So this is the value of local Lipschitz constant and x. In the case when our space is Euclidean, say, right, it will be exactly square of the norm of the gradient. For if functions differentiable, it will be square of the norm of the gradient. Okay. Okay, so this is local Lipschitz constant. I will assume that psi is normal with mean zero and variance sigma. And then, the following inequality, it's kind of can be derived from standard Gaussian concentration inequalities for standard normal random vectors, right? Or can be proved independently using some arguments with which these inequalities are derived, like this is Moret-Pisniak concentration inequality. Okay, you basically can show that G of psi minus expectation of G of psi, the LP norm, will be controlled this way. You see here the square root of P that tells us that we are talking about there is already some Gaussian type of concentration that is happening here, but then there is the LP norm of the local Lipschitz constant at psi. Okay, local Lipschitz constant and so. Now, if our functional is Lipschitz, right, which means that local Lipschitz constant is bounded by a number, right, which is Lipschitz norm of functional G, right, global Lipschitz norm, right, of functional G, then we are getting this inequality. I can, since there is a square root of P here, if I take divide here by square root of P and take supremum over P, this will be psi 2 norm. Exactly some Gaussian norm, and we have just one of the ways to write Gaussian concentration in this case, okay? That's what is happening here. Now let's try to use it. Yeah, I cannot, I missed the slide for some reason, but this is what I am trying to prove, okay, and I jumped immediately to Gaussian concentration inequality, but that's what we will prove, okay? Okay, we discussed kind of generalities about Gaussian concentration inequalities, but now let's see what we will try to prove. We will be looking at this Gaussian location model with an observations, right? And we will use the sample mean as our estimator of location parameter theta, right? The sample mean is an estimation of the parameter theta, and based on the sample mean, we will create this sequence of functions fk and create estimator fk of xn with bar. Okay, is the way we define it, right? This will be our estimator that we will study. Okay, it's an estimator already with kind of reduced bias. And then I will assume that S is k plus 1 plus rho for some rho between 0 and 1. So F is in Hilbert space CS, okay, in Hilbert space CS. And then this is what we will get for this estimator, right? That the for any loss that is like psi 2 or smaller, right? You will get this bound, right, on the orange norm of k of xn with bar minus f of theta, and there are two terms in this bound. One term is roughly of the order 1 over square root of n, and another term will be of the order g over square t over square root of t over n to the power s. If we view square root of this log of psi square as d. Okay, so it will be more in terms of effective rank, right? So if we are in the case of standard Gaussian noise, it will be just the square root of d over n. Okay, so this is the type of bound I claimed at the very beginning, right? We have some lower bound, okay, and this is type of bound we want to achieve with these problems, okay? And that indeed gives us this type of bound. I rewrote it here, you know, just for mean squared error. Okay, for mean squared error, in this case, it will be exactly d over n to the power s. If d is the effective rank, okay, in this case, okay, because we are dealing in covariance, which is not necessarily spherical, the problem could be infinite dimensions. General version of this problem. Okay, but we are getting the error rate of you know that we want to get. Okay, using this method. The group of this kind of one part is bias reduction in order to obtain a bound of the bias of this type, and this is what we already discussed. The bound of the bias of this type will hold in this type of problems, right? And another part is concentration. Okay, and this is what why we are talking about concentration. Okay.
Can I ask you a question?
Yeah.
About the previous slide.
Previous one. Okay.
So one,
I think it's the next one because you have skipped it.
This one.
the one with the local limits constant
60.
calculation.
Ah, okay. Okay. This one.
Yeah, I couldn't quite catch what U was.
Sorry.
What U is it?
U is you can view it as an arbitrary ball, okay, the center, and taking more and this.
Okay, ball with like one radius one.
The ball of arbitrary radius. Okay, you can make radius of the ball small because you want it to define its constant at point x. Okay, more of the response. Okay. Okay. Okay, so now how do we prove this? Okay, how do we prove this result? Okay, so first of all, you know, let's recall that when we kind of talked about some ways to obtain analytic properties of function fk, okay, which be useful is this integral representation of operators b to the power kf, right, and stuff like this. And then it is possible to prove that the Lipschitz norm of fk will be upper bounded by c1 plus rho norm, and this norm is bounded by cs. Okay, we had this type of bounds at some slides that were last time. Okay, when we discuss this type of problems. Okay, so we have this property in the case of location model, say, right? We also have this bound on the bias. Okay, so basically we discussed the way to draw this bound on the bias in the case of location model. Okay, so we have this bound on the bias. Okay, and what is left is to study concentration of our estimator around its expectation. Right, our estimator is xn with bar, that we can write as theta plus psi n with bar. So this is the average of the noise, right? Of the noise. And psi n with bar is equal in distribution, right? Since these are Gaussian random variables, they are identically distributed, right? It will be equal in distribution to psi divided by square root of n, right? Psi divided by square root of n. As a result, if we apply this is Lipschitz function, right? If its Lipschitz constant is bounded by CS, right? If we control psi to norm, some Gaussian norm, we will get this vector, and we are getting one over square root of n because the noise in our problem is kind of like psi divided by square root of n instead of psi, right? So the covariance will be scaled, okay, then like this, and we will get this one. Okay, and this is what we need in order to prove this result. Okay, so that's a positive extension. Okay. Now, what other things we can prove here? Okay, so it follows from this bound that I stated, right? That you know, kind of things that I already mentioned last time. There is a phase transition on the rate depending on how large the effective rank is in this case, right? if it's like n to the power alpha, then S is greater or equals than 1 or 1 minus alpha, we will get n to the power minus 1 rate of convergence for the mean squared error. And in the case when our Banach, and if R of sigma is larger than n to the power alpha and we don't have enough smoothness, we will end up with slower rates than n to the power minus 1. So there is kind of standard phase transition in this type of problems. And the bounds we obtained are sharp in this example, okay? Just an example of standard normal vector rescaled with some sigma, right, as our noise, right, when one space is RD and it's equipped with Euclidean. In this case, this is sharp because there is this minimax lower bound that actually follows from this minimax bound that I stated is a first lecture. Okay, you can try it from there. Okay, so we have this type of properties. Now, the next thing we can obtain some result about normal approximation of the error of our estimator, okay, of the error of our estimator. It's a result about normal approximation because this random variable that we have here is already normal. It's a linear function of something. Only one-dimensional normal random variable, so there is this result about normal approximation. Okay? Let's discuss how to prove this type of result. You see here what is happening here. If this is like dimension, okay, or square root of the dimension, in this case, right? You have here something like square root of d over n, and if d is for small of n, right? If d is for small of n, then the whole thing. And if S is sufficiently large so that the second term is smaller than 1 over n, or 1 over square root of n in this case, right? Because I have square root here, right? Then in this case, the size of this error of this approximation will be smaller than n to the power minus 1/2. Okay, smaller than n to the power minus 1/2. And the size of this guy by standard work with Gaussian random variable will be of the order 1 over square root of n, right? So it means that we have kind of, the distance between these two things is smaller than the thing with which we are trying to approximate. Okay? So that's kind of result and almost to establish efficiency of these estimators. I kind of stated some facts that follow from this when the threshold of smoothness is above this, strictly above this level, 1 over 1 minus alpha, you will have basically convergence if you renormalize this with square root of n from this inequalities. I stated it will follow that the thing converge to normal distribution, for instance, in Wasserstein distance, okay, it can be proved in Wasserstein distance or in some other distances, it does not matter much. And also you will have convergence of this guy to the limit variance, essentially, okay, to the limit variance in this case. Okay, and this is enough to prove efficiency, okay, of this method in this sum. Okay, so basically we have kind of the whole picture that we wanted to have, okay, in the case of this type of problems. Let me discuss very briefly how to prove this normal approximation bound. It again relies on Gaussian concentration inequalities, okay, in some way. Namely, this time we need to study the following problem. We are looking at the first order remainder of the Taylor expansion for smooth function G. Okay, we are looking at this guy, and what we are interested in concentration of this first order of the remainder of first order Taylor expansion, but we replace H, right, the increment by Gaussian random variable sign. Okay, a Gaussian random variable sign. In order to study this problem, we need for this function viewed as a function of H, basically to compute or to upper bound its local Lipschitz constant. That all that is needed, then we can write concentration inequalities using the method I discussed, right? Using the method I discussed. So it's not hard to show that local Lipschitz constant in this case will be basically equal to this norm. Okay, will be equal to this norm, or at least upper bounded by this norm. I don't remember whether it's precisely equal, but it will be made upper bounded. And then in turn, it will be upper bounded by Lipschitz norm of the derivative, right? Times norm of h, right? Times norm of h. If we use this fact, right, we can start writing inequalities here because what we need to write, we will need to write LP norm, right? LP norm is the right-hand side of local Lipschitz constant, right? Which, if we pull out this type of stuff, will boil down just to LP norm of the norm of Gaussian random vector, right? And this, the norm of Gaussian random vector is already Lipschitz constant of Gaussian random vector, so we can use concentration inequality another time. Yeah. So basically, we are replacing now this guy at the next step by its expectation, right? By its expectation and do concentration here. Also, right, as a result, we will get already not Gaussian concentration, but Bernstein type concentration, right? Bernstein type concentration given by these bounds and will be bonds. Okay? Given by these bounds and will be bonds. And if we apply it to what we are interested in, to this thing basically, right? So that's what we need in order to prove normal approximation. We can rewrite it as one term that corresponds to the concentration of the remainder of Taylor expansion, right? And for this term, we can get upper bound. We have to take into account that we know analytic properties of this function fk. I can control everything in terms of the norm of f, right? Functional itself, and we will get upper bound on this form. And for the second term, you remember that the first term in the series or in the sum that defines fk was f of c, right? If you look at the difference between fk prime of theta and f of theta, we can upper bound this, right, using this bound that we essentially are in possession. Okay, at this point, right, and this will give us the bound of the same order actually as for this term, but together this gives us this inequality that I stated. Okay, that I stated. So that's basically some gain with concentration with. Okay, so this gives us certain roadmap that can be used to study other problems, okay, more complicated problems too, because this was kind of relatively easy to do concentration of this problem. It was Gaussian setting, and estimator that we used was x and with bar, which is kind of simple, explicitly defined estimator. Okay, so it's kind of was easy to apply Gaussian technique. This is a bit more complicated example of the same topic. This time I am talking about log concave distribution, and the goal is to estimate location of log concave measure. So we have some log concave distribution, so it means that the density of this, it's in RD, the density of this guy is e to the power minus v, where v is convex function on RD. Okay, that's log concave density. Okay, and then we change location of this density, right, and create a location family. Right here on the location model. Okay, location model. We are assuming that we know this v in principle, okay, but we don't know the location, and the goal is to estimate functionals of the location. Okay, functionals of the location. So. Based on IIT copies of random variable x sample from this distribution we need some regularity conditions here, primarily because I want to get at the end estimators that will be also efficient. I want to implement completely in this context Fisher's program, okay, to have a asymptotically efficient estimators, okay. So the regularity conditions here as our standard, we will assume that V is strictly convex and twice continuously differentiable. There is unbalance on derivatives. An interesting condition is this. If we look at this matrix, that will be exactly Fisher information matrix in this problem. Okay, Fisher information matrix in this problem. I want this matrix to have eigenvalues that are bounded away from zero by constant n. Right, so it's kind of non-singular matrix in strong sense. Right now. If I assume, right, that the Hessian, okay, of B, the second derivative, okay, is a matrix valued function where kind of bounded away from zero in strong sense, in the sense of matrices by a constant, right, this would be very strong assumption, okay, because under this assumption, basically our log concave distribution becomes very similar to Gaussian distribution, and it will have Gaussian concentration. But under the assumption I made, we are assuming only that the average of this thing, right, is bounded away from zero in a strong sense, right, in the sense of matrices. But it does not mean that that we have this property at each point in the space. Okay, that's why we are still in the domain of concentration of log concave measures that is more complicated. Okay, so that's basically the assumption that we are making in this problem. Now, well, what are the results it's possible to obtain here? In this case, you can characterize this solution of this max what was it? Max problem. Okay, that I stated on the very beginning, right? We can characterize this solution precisely, so to up to numerical constant, basically, this will be of this order, okay? This will be of this order. Not numerical constant, probably constants that depends on this regularity conditions, okay, that we impose. Okay? This constant and all the regularity conditions. This will be of this order, and this is exactly the rate we already expected, this problems, right? So that will be correct rate. And the lower bound is a consequence of the bound that I stated in the very beginning, right? So the upper bound requires the construction of the estimate, okay? The construction of the estimate. Okay, so it's already standard, it implies space transition at the rate from slow to fast. Now, how we are going to construct the estimator? In this case, the base estimator will be in this problem maximum likely estimator that boils down to minimizing this sum. So it's a convex optimization problem. Okay, since V is convex function, estimator is defined as a solution of convex optimization problem in this case. Okay. Now we will use it as a base estimator, and based on this estimator, we define this function of fk, okay, by these iterated bootstrap ideas. Okay. We define this functional fk, and then fk of theta and hat will be used as an estimator of f of c. Okay, as an estimator of f of c. Now, the main result you can prove about this estimator that implies everything is this theorem. Okay, is this theorem that tells us that it allows us to get bounds on the risk of this thing, and it at the same time allows us to get approximation of the error in terms of the sum of independent random variables, right? It allows to do normal approximations, okay? It allows us to do normal approximation. Here there is an interesting Orlich norm with exponent to source, okay? Not even psi1, so kind of bigger than some exponential things, okay? There's some exponential tails, but this exponent which is bigger than 1, okay? Smaller than 1. Okay. Okay, now the size of this bound you can see will be smaller than 1 over square root of n, right? It's immediate that it will be or small of 1 over square root of n, provided that d is or small of n. This is what is needed in order to achieve normal approximation, right? If d is less or equals than n, we will get 1 over square root of n1, right? 1 over square root of n, right? Okay, but if t is smaller than 1 over n and the second term which comes from the bound on the bias, okay, is negligible, then in this case, we are getting enough for normal approximation, okay, because the size of this fellow will be 1 over square root of n, right, but the central limit 0. Okay, the central limit 0. Okay, so what is happening in the proof of this result? Okay, this part is obtained more or less using similar consideration to what we did in the case of general location models. Okay, it's bound on the bias. Okay, bound on the bias. The rest is related to concentration. So basically, we need to replace f of theta by expectation of fk of theta f, right? Okay, we need to replace it by this and prove the inequality for this, right? And this requires the use of concentration inequalities the same way as we did in Gaussian case. Okay, we had to deal with similar problem in the Gaussian case several minutes ago, right? Several minutes ago. So one part is proof of the bound on the bias, which leads to this term. If I, instead of this, put expectation of this guy, this term will disappear and I will be left just with the first term. So, well, okay, this is where it comes from. Okay, so concerning, again, bound on the bias, it's more or less a repetition of the standard argument because maximum likelihood estimator is equivalent estimator. Okay, so we can use this type of formulas that we used in the case of equivalent estimators. There are some technicalities here because we can't use them exactly the way they are written, but it's not the features. Okay, kind of a more complicated part of the proof is the proof of concentration. Okay, and well, basically what we need kind of to prove concentration of the remainder of first order Taylor expansion, as we did in the Gaussian case. Why it is more complicated than in Gaussian case? Primarily because we are using estimator, okay, not the sample mean, but estimator that is defined implicit, okay, as a solution of optimization problem. And then things like bounding local Lipschitz constants for this estimator and stuff like this becomes more complicated. There are certain truncations that we need to do on the way in order to make it work. Okay, so it's just a lengthy argument, but the roadmap is the same as before. Okay, the roadmap is the same as before. Now, there is this constant involved in the bound. This is what is called Poincare constant on the distribution tree, because the main tool to prove concentration and inequalities for more concave measures, okay, is Poincare inequality, and yeah.
Why do you get the 2/3?
These are some losses related to control of the local Lipschitz constant of the estimated. Okay, otherwise we could get psi, okay, which would be typical for local problems. But here, you know, this also take into account this remainder of Taylor expansion. Okay, so there are losses here, inevitable losses. Okay.
Thanks.
Okay, so now Poincare constant is defined this way. Okay, it's the smallest constant for which Poincare inequality holds for all locally Lipschitz functions. Okay, this Poincare constant of probability measure. In the case of concave measures, you know, in the case of any measure, in fact, Poincare constant is always larger than the operator norm of the covariance operator. Okay, for this problem it's easy to check. Okay, but in the case of log concave measures, there is a long-standing conjecture by Cannon, Wolosh, and Simonovich, KLS conjecture, according to which the Poincare constant up to numerical constant and bounded from above, the operator norm of the covariance. This is unsolved problem so far. Okay, also there has been lots of progress in the recent years. So general belief is that it's a numerical constant. But in 2020, there was a breakthrough result by Yuan Si Chen, who was able to prove that if you can write this with constants that depends on the dimension, like d to the power epsilon for arbitrary epsilon larger than 0. In fact, better than this with some logarithmic type of factor, okay? You got some logarithmic type of factor. And the best is, since then there were some improvements, and the best dependence known now is square root of log d. Okay, square root of log d. But even the way it was in the UNC-Chen constants happened to be sufficient for us to achieve our need. Okay? So it's kind of very big dependence on the dimension that probably is not needed, okay, but this is an open problem. Okay, now you can, yeah, so this is, I stated here some examples about convergence of the variance and kind of normal asymptotic normality of the estimator. This is relatively straightforward problems from what I said. Now, a natural question to ask is why not to use in this problem extend with bar as an estimator rather than a maximum likelihood estimator. In fact, if we use extend with bar, we can prove exactly the same rate, exactly the same upper bound of the rate, same structure of the rate, without much regularity conditions. Okay, it's not needed. Okay, the case of extend with bar. The problem becomes simple. The case of extend with bar. The only reason, so this is same. Okay, the only reason to use maximum likelihood instead of extend with bar is just to be truthful to Fisher's ideas. Okay, to achieve asymptotic efficiency, to have correct limit variance. Okay, for estimator based on the same approach and with base estimator extend with bar, it's not going to be efficient. It's its limit variance will be something. Okay, that's why. Okay. And of course, the real reason was that it was more interesting problem to play with because there were more difficulties involved, but the motivation for business just to do what Fisher wanted us to do. Okay, so there are various questions that are open in the case of irregular application families, but I will probably skip this. And I will move to the last model for which something was done using this method, as I discussed. Okay, and this is general normal model in RD. Okay, general normal model in RD. So we are looking at IAD observations. The unknown parameter is mu sigma, where mu is mean and sigma is covariance matrix, right? So now we will use kind of equip the space of parameter with the norm, which consists of two parts. One part is the just usual Euclidean norm on the vector component, right? And on the matrix component, we will use operator. Okay, we'll use operator norm. And with respect to this norm, we will be considering everything. We will be considering smoothness classes, you know, this notion of Gaussian smoothness and stuff like this. Okay. Now, as an estimator, we will use the sample mean and the sample covariance, right? Defined in a standard way. For this problem, it's easy to get this bound, right? For this estimator, right? So it's kind of bound with standard dependence on the dimension in this case. Okay, and now this is the result we were able to prove in this case. We had to look at the class of parameters, at the set of parameters. This will be our parameter space, which is RD, so there is no constraints on the mean. Okay, there is no constraints of the mean. And as far as covariance is concerned, we are looking at covariances whose spectrum is bounded away from 0 and bounded from above. So it's between 1 over A and A, or some A greater or equals than 1. Okay, it's kind of spherical covariances. Okay, spherical covariances. So we could not allow eigenvalues of the covariance to go to 0. Okay, to go to 0. And in this setting, we are getting this bound on the error, right? In psi norm for any psi which is smaller than psi 1. So what is happening here. That's what is happening here. Now, what is involved in the proof and why we could not go beyond this case, okay? Beyond beyond the case of covariances with spectrum bounded away from zero. The main difficulty is that we rely on this random homotopy method, okay? And as I already mentioned, random homotopy that is natural to use in this case has this form, and there is sigma to the power 1/2 square root of sigma involved. And if spectrum of sigma is allowed to come close to zero, we are losing Gaussian smoothness of this homotopy, okay? We are losing Gaussian smoothness, and then the bounds that on which we rely would collapse, okay? Would collapse. And this is a difficulty that I don't know how to overcome. I spent some time seeing whether there is a way to overcome it, but I don't know. Which doesn't mean that that someone else could come. It means that I wasn't able to do it. Okay? I suspect that in order to overcome this difficulty, you need to analyze the problem differently and maybe to forget about the whole machinery of random homotopy and of this representation, do something else. But how to do it, I don't know. So for this type of estimators, we don't know how to do patterns and under this assumption. Okay? Under this assumption. So, I was disappointed with this and decided to check whether other methods would give correct answer without this type of assumptions, okay? Without constraints on the covariance, and it happens that there is a method that does it, okay? Does the job. So I could have claimed, like statisticians usually do in statistics papers, you often can read that method B is much better than method A, because for method B I prove this very nice bound, and for method A I prove only this bound. Okay, it's it's kind of questionable argument. Okay, because you can there are at least two plausible explanations. One is this explanation. Another explanation is I am not good enough to prove it for method A, but I am good enough to prove it for method B. That's, so in this case, I don't know what the correct answer is, whether this type of method, just there is something intrinsically bad about this method that do not allow to handle this problem, or I'm too old and lazy to do this. Okay? Yeah.
We're looking at Gaussian case here. So why is the result psi1 and not psi2?
Because this is because so the sample covariance is quadratic.
Oh, okay.
That's why we are using indicating this thing. Okay, so there are, there is a lot about there are space transitions, there are various coordinates that are set. Okay, we still have 10 minutes, so we can start the next thing, and this will be another estimation method. This is the estimation method I at the end used in the case of the problem of estimation of covariance of functionals of covariance metrics, of covariance operators, okay, and this is what we will discuss tomorrow, okay, but the method itself I can discuss maybe, so I will start discussing now, because this is kind of a rather simple method, actually, and it's also a common method in statistics, okay, it's kind of, I already mentioned it briefly, but now we have to discuss it in something there. So I will be talking about methods of bias reduction now that are based on this idea that you on a different idea. So that you look at several plug-in estimators with different sample sizes. So you take subsamples of your sample. Actually, in this problem, it does not matter that the subsamples intersect or not. You just don't care about this. It could be dependent. Okay, not a problem. Okay. So you take some subsamples of certain sizes, right? and you take plug-in estimators with these sample sizes, and then choose some coefficient Cj, right? Choose some coefficient Cj, and trying to choose Cj and Nj in such a way that biases of individual plug-in estimators cancel, okay, or almost cancel. Okay, that's the idea of the method. Okay, so in which situations this could be done? Here is some framework, some general framework in which it's easy to accomplish this goal. And this is a framework when we have some random variable I, sampled from distribution in a Banach space E with a known mean. Okay, so the mean is a known thing for this random variable, right? And then we have a functional defined on our Banach space, and our goal is to estimate the value of the functional at unknown mean. Okay, so there is no parameter here, but there is mean. There is that is of interest to us, and we are trying to estimate the value of the functional at unknown mean based on IAB observations. Okay, so what is the main fact that allows us to invent here? It's not me who invented this, it was invented long ago, and so the version of the method that I am discussing was in this paper of this two Gaussian IEEE on information series that I mentioned last time that dealt with binomial high-dimensional models at all, okay, but it's certain version of estimators that exist in statistical literature. Okay, so the main fact that allows us to do it is the following: that if we have, for some k greater or equals than 2, if we have functional f that is k times differentiable with the last derivative satisfying Kölner condition with exponent rho, okay, with exponent rho, and if expectation of the norm raised to power k plus rho of random variable y is finded, then you can write a simple representation for the bias of plug-in estimator f of y and bar. Okay, so we write expectation of f of y and bar minus f of expectation of y, right? And it will be represented as this sum of k minus 1 term, where you have powers of n, and you have coefficients that do not depend any longer on n. This is very important, right? We kind of removed all dependence on n. It's in these powers, right? The coefficients do not depend on n. And there is a remainder for which we have this control. Okay, for which we have this control. This control of the remainder should be sufficient for us to kind of remove bias. We just need to get rid of the first part, right? Get rid of the first part. In the case when f is a polynomial, by the way of the case, and there is no remainder, so r will be equal to 0. In this case, it will be just representation of the bias. So this method will give you unbiased distribution. So the proof of this is very simple, and if you take it as a problem, you have to use Taylor expansion, of course, and do some computation of expectations. This problem, which is okay, but it's easy to do in this setting. Estimator is sample mean for some population. Okay, otherwise it might be very hard. If you try to do it for maximum likelihood estimator, we used in the previous problem, okay, it will be practically impossible to. Okay, to study this method. Okay, but we have this nice property, and what do we do next? Next, we are taking some sample sizes N1 and K that are different, but all comparable with N. Okay, all will be comparable with N up to 1. Okay, so we have N observations, but we choose this. We don't care about the samples will be intersected. Okay, it doesn't matter. Okay. Then we create this estimator that I mentioned based on sample means, based on samples of size nj, and then we choose coefficients satisfying these equations. Okay, there are k linear equations, right? And the system of these equations will have solutions. Okay, with the first assumption is more or less clear. The sum of coefficients would be 1. The rest are some orthogonality conditions, if you will. Okay. And if you solve the system of equations, the solution will be just using Cramer rule. The solution will be this. Okay, it's given by this form. Okay. Now we need one more constraint is needed on the choice of the sample sizes. Okay. We want the sum of absolute values of this coefficient, they can be positive or negative, okay, to be bounded by a constant that depends only on n. Okay. This is not always the case. One of the popular choices is to choose just two samples, one of size n, the whole sample, another one of size n minus one. In this case, this would be bad because the coefficients in this case, so to choose coefficients that will be equal to n and n minus one. Okay, this is one. Well, one popular choice. One will be n and another one minus n. Okay. And this is bad because the sum of these coefficients is one, but the sum of absolute values is large. Okay. What we need basically the difference between nj plus one and nj to be also of the order of n. So you can use kind of geometric progression, okay, some q, and then this will be satisfied. Okay, that's the way to choose this guy. Okay. Okay. Well, why all this works? Okay, this is the proposition that one can prove. Okay, that the bias of this estimator will be controlled just by this higher order terms. Okay, higher order terms because we are raising the norm of the error, right, to power k plus 1. Okay, so as a result, it becomes small. Okay, as a result, it will become small if the smoothness is symmetrical. Okay, so why this is true, I will just show you this maybe slide or figure, okay? Because I think my it's well, we have 2 minutes to be precise. Okay, so if you look at our estimator, right, you can of course write this in sum of the coefficients is equal to 1 in this form. So the bias of this estimator will be sum of the biases of individual plugin estimators multiplied by CJ. Then for each of these biases, you use this decomposition that we had, right? And then, as you see by our choice of coefficient, right, we will have cancellation. Okay, so this, with exception of the number, right, everything will cancel out, okay, because the sums are conveniently chosen to be zero. Okay. To be zero, as a result, this terms cancel out. You are left with just with linear combination of the remainders, and then since the sum of the absolute values of coefficients is bounded by a constant, you are ending up with this upper bound. Okay, ending up with this upper bound. Okay. Moreover, you can easily handle in this case concentration inequalities. Okay. These estimators, because you just have to write this basically, right? That an LP norm of the difference between estimator and its expectation will be upper bounded by sum from j equal 1 to k, right? Of LP norms of individual of concentration of individual plugin estimators, right? That's what we have, okay? And then since this sum, okay, again, we have this convenient condition that this sum is bounded by a constant that depends only on k, right? We are ending up just by the maximum of these guys, right? So kind of what follows from this is that to bound this LP norm, right? It is enough to bound basically 2 things, to have an upper bound on this. All sample sizes we are using are of the same order as n, so it does not matter, right? But we need an upper bound like this on this norm. This is to control remainder, and to do concentration, we just need to have concentration inequality for f of y and this bar around its expectation. Okay, around its expectation. 2 things are okay. So the only things that we have not achieved yet, and we will achieve, I will show you this few slides next time, is how to achieve efficiency in this case. Okay, this estimator is not going to be efficient. Okay, that we create in this way, but a simple modification that is equivalent to what is called in statistics jackknife version of this method, okay? Already will give you efficiency, okay? And it's shown in the next 3 slides, maybe I will do it next time, okay? And the main thing that we will do tomorrow, we will show how to use it to estimate certain estimating of type of smooth function or covariance operators. Okay, this will be our main problem next time. Okay, see.
Any questions?
So we divided the algorithm to different parts. So you mentioned divide them in like geometric phase.
Yeah.
But they do take on your boundaries, maybe you're dividing them.
No, I need and J plus 1 rate to be able to say in others. That's the control up to small box of the up.
Or the will be putting them at many months divided by one.
And the one with where constant, well, you come to check, well, let me try to find. Just a second. Fine. Really. Let me look at the how the coefficient look like, okay? This is how the coefficients look like, right, in this problem. So you have to check whether this product, right, whether the sum of these guys, right, the sum of these absolute values will be bounded by a constant. In this case, is going to be bounded by a constant if you choose the way you suggest.
Yeah, but it's like J times n divided by a constant.
I'm not sure because, okay, maybe, okay, yeah, just check, okay, but I know for sure that we can choose a geometric progression, that's no problem. You can check, but I don't think it will, but it's not.
Maybe not, yeah.
Okay, so just check it, okay, but it really does not matter for me, whatever choice such that the sum of absolute coefficients is bounded by constants. Also important to have specific choice. For me, something for you who's using it. Okay.
Any other questions? Thank you.
So tomorrow is the last day of the summer school. We have one more lecture by Cindy and one more lecture by Vladimir. So 9 o'clock, same place.
Here.
Yeah. You have a nice break tomorrow.